Hello, viewers. Consider a data center environment where lot of cloud computing environments are there. High performance computing is there. Storage devices are there. Routers, switches. A lot of communication devices are there. In between these devices, loads of data are transferred. Terabits, petabits of data are transferred. What is recommended for a data center is a large amount of data will be transported between the devices, efficient data transport, and the third one is ultra low latency. So these are all the three prime characters for a data center. So in order to achieve these three characteristics, we introduce the parallel optic technology. Okay, consider a data center. For example, this is core switch one, and the second one is core switch two. Both switches are connected through a fiber, single mode fiber, which is having a bandwidth of 10 Gbps. Okay, let's see how data is sent across this single mode fiber. So data is transported from core switch one, segmented into four pieces, and they sent into sequence one after the other. The core switch two receives the in the same sequence. And then process it and retrieves the data from the packets. So this is what happening in the serial communications. Okay, let's see the another scenario. Now the server it requires a more bandwidth. It requires a data transmission in terms of petabit. A single fiber is not sufficient to cater this bandwidth. So what we are doing it, we are running multiple fibers between the two communication devices. For example, we can serve, say, two servers in the data center. Okay, now each fiber is having 10 Gbps of capacity or bandwidth, we can say. So now how data transmission is happened here. For example, same way, the packet is coming here, segmented into four parts and sent into different fibers. Instead of sending into one single fiber, the pieces are sent into different fibers, and the receiver receives all the four pieces from different fibers, reassemble it, and then decode it and retrieve whatever information it wants. So, what is the benefit of using parallel optic technology? The first thing is bandwidth. Earlier, we used single mode fiber with 10 Gbps capacity. Now we are running 10 fibers. So 10 into 10 Gbps, 100 Gbps capacity we are getting it. And the second one is scalability. If you want to increase it, you can simply, just like that, we can add multiple fibers between the two devices. And the third important thing is ultra low latency. So earlier, if you want to send 10 GB of data in a 10 Gbps link, it required 1 second to send the link. But now we have multiple 10 Gbps links. For example, we have 10 fibers, so the total capacity is 100 Gbps per second. So 10 GB data is transported into a 100 Gbps per 100 GB per second links. So it will be sent very faster, almost more than 100% faster than the 10 Gbps links. So that is the advantage of low latency, which is very critical for a data center environment. The fourth one is efficiency. So efficiency here we are talk about how much power is required to send a bit. Okay. For example, when you are using single mode fibers, if you want to transfer high speed data or high bandwidth data, then you need to use higher modulation schemes and high laser powers. And then also it requires a lot of complex electric circuits. So this way, it increases the cost of sending one bit between the devices. But here we are not using higher modulations. We are not using high power lasers. We are so the circuit is very less complex. So the efficiency is quite high. And then how it works, how the data packet is segmented and it is sent across multiple fibers. So it requires a special type of protocol, right? So what are all the protocols? InfiniBand, it's a famous one, and Ethernet fiber channel. These three are there. InfiniBand is used in between high performance computing environments, particularly which requires high performance, low latency environment. We can say to be communication between two servers, two routers, two switches, like that. And the Ethernet, we can use it for communication between routers and switches. Of course, we can use the same standard Ethernet protocol because now all the standard Ethernet protocol like 40G and 100G has the technology or protocol which is embedded into the standard definition, like sending the data across parallel optical links. And the third one is the fiber channel. The fiber channel is another protocol which is predominantly used between in SAN networks, storage area networks. Okay, now we are good with the protocols, how it will. Let's see how it is connected. We imagine how we go how we are running multiple fibers between these two. It looks very clumsy. Handling these fiber is very difficult. But that's how these connectors comes into picture. The MTP and MPO connectors. So MPO is the basic connector, and from MPO, the another connector MTP evolved. MTP is basically a brand name. It's called US Connect, which comes from MPO. It's more flexible than MPO, and it's used in high performance environment. High durability. That's the difference between MPO and MTP. So what these connector do? If you look at the physical connector, it contains fibers from 12 fibers to 72 fibers. You won't feel that there are 72 fibers are running in one single connector. So let's see how the connector looks like. This is one sample connector. For example, here you can see there are 12 fibers are connected in this one. These are the termination points. This is one type of MPO connector. Okay. So if you look at MPO and M2, MTP connectors, both are looking very similar. You can't typically find any difference between MPO and MTP, but still there are a difference out there. The primary difference is the like ferrule. Ferrule is what the surrounding material of the fiber. So it might be a ceramic or high plastic material. So this ferrule is somewhat kind of fixed. You can see that enclosure. It is fixed in an enclosure, so it is a little bit stringent or tough to handle. So if you fix it, then there will not be any flexibility. But it's good. But other ways, if there is a strain in the fiber cable because of the environment, then it may not be shootable. It's not very flexible. It is very sturdy. On the other hand, if you come to MTPs, there is a no enclosure, or so it's all are flexible. And if you look at the connector type end, I will see in the next slide. Okay. So in the MTP, it's like a curvature type. What they said, according to the physics, it's so flexible compared to this type of flat connector ends. It's flexible and sturdy. We can say the wear and tear is quite low in this MTP connector compared to this one type. Okay. And other than that, what all the difference between the two connectors is MTP comes with the metallic things, metal for pins and all. Okay, it uses empty ferrule. As I said, it comes in a enclosure, but here it is a floating ferrule. And then other than that, we have discussed everything. Yeah. Okay, now I have two questions. You may ask why we can't use DWDM between these two servers or high performance computing servers. Now, yes, we can use DWM very well, but imagine we already told that parallel optic technology is used only in data centers where it requires high performance data transfer, high volume of data, and efficient data transfer, and then ultra low latencies. But still, DWDM, if you want to deploy a DWDM within 100 meters distance, the initial cost to set up a DWDM infrastructure is high, and the infrastructure cost is also high for DWDM. We are using multiple wavelengths, separate circuits is required, and it's for a shorter distance. It's not required. Instead, we just plug in 12 fibers inside. inside the like, and also the if you want to increase the scalability, when you talks about, of course, you can introduce another wavelength, but again, cost is involved in this one. Reduce the latency. DWDM doesn't deal with the latency part. It still follows the serial communication. But on the other hand, parallel optical technology, data is segmented and transferred across multiple fibers. So the latency is reduced and efficiency. Yes, the cost of sending a bit is high in the WDM because of the electronics involved compared to the parallel optic technology. And another question in the reverse order, why can't we use this parallel optic technology in long distances? For example, this is one state, this is another state, and why can't we use it this one again? So if you are running 10 fibers between two states, for example 100 miles apart, then you have to run 10 fibers. Infrastructure cost is involved, which includes the fibers, amplifiers, and what the electronics between optical electrical conversions, all those things. And obviously we have a trouble in fiber optic technology, that is attenuation and the signal dispersions, like CMD, chromatic dispersions. So this is handling this dispersion is a challenge in serial communication as well as in the parallel optic technology as well. But the major challenge in parallel optic technology is you are sending the bits in different fibers. So in the receiving side, you have to reassemble it. Reassembling or decoding on the information is very tough when you are dealing with attenuation and dispersion in parallel optic technology. And scalability and flexibility, of course, there are plus and minus in both sides. If you are using scalability, you have to run another fiber between from here to here. Obviously, 80-kilometer fiber is more costlier. 80, 100 miles fiber. Instead, you can just like one add on one wavelength in the same circuit if you are using DWDM. Um, that's the thing. I hope you enjoyed this one. And all this information is available in our website, Explore N2P. You can find some additional materials and question and answers in the website. Please refer our website. Thanks for watching.